Hello, in example 2 here, we're going to find the area between these two curves, h of x equals x squared plus x plus 1, and j of x is equal to 7. Now notice, unlike example 1, I'm not specifying what the actual limits of integration are. And the reason is pretty simple. We need to draw a picture to see what's going on, and what we can see then is that if we draw the function j, it's a flat line. It's y equals 7, so this is a flat line. And h is a parabola with this shape in red. So knowing what we do about lines and parabolas, we know that the area between those two functions is strictly right here. And what that means then is that we have to determine what the limits of integration are from determining the points of intersection. So we have to integrate from this point on the left to this point over here on the right. Now it looks like, just from the scale of the graph, this takes place on the right at x equals 2, and it takes place on the left over here at x equal -1, 2, and -3. We're going to verify that in a moment, but we just need to keep in mind that in order to do the integration and to find the area between those two curves, we need to know where they intersect. So as you can see from the picture after we draw it in Desmos, the upper function is the flat horizontal line. So the upper function is j, and the lower function is h, because the blue j function is above, greater than, the red parabola function in red on this interval here. Right? So the integral that we're looking for then is going to be the upper function, j, which is 7, minus the lower function, which is h, all dx. Now notice I've put this subtraction symbol here, and I've been really careful to subtract in parentheses the entire function h, because if I don't do that, and I don't distribute the negative sign into all three terms of this function, I'm going to end up with some sign errors. So be careful when we do that. All right, let's keep going. We now need to find the limits of integration. Now visually, we can see that it looks like they take place at points A and point B, which are these points here. And we think that those points are -3 on the left and +2 on the right. But we don't want to just guess. How would we know for sure? Remember that two functions intersect when they're equal to each other. So I can set h equal to j and then solve for the value or the values of x that make that true. Two functions are equal to each other algebraically when they cross each other on a graph. So when I do that, when I set h on the left equal to j on the right, and then subtract the 7 from the right side because we have a quadratic, so we need to have 0 on the right, we end up with this quadratic, which is conveniently factorable. If it were not factorable, we would need to find the limits of integration using the quadratic formula. And so we would have to get an estimate rather than an exact value. But in this case, it factors as x plus 3 times x minus 2, right? Because +3 times -2 gives me -6. And the sum of +3 and -2 gives me +1 for the coefficient of the x term in the middle. So I have this factor times this second factor is equal to 0. And we know from previous algebra courses that means that we can solve for x plus 3 equals 0, which means x is -3, right? That's the left limit of integration right here, so we were correct. And then we can solve x minus 2 equals 0 and get x equals +2, and there's the right side limit of integration. So if the limits of integration are not given to you, you're going to need a graph, and you're going to need to look at potential points of intersection. So let's go ahead now and integrate. We're taking the upper function j minus the lower function h. Let's do a little bit of careful algebra. The negative sign gets distributed, so we have -x squared down here. The negative of +x gives me -x, and the negative of +1 gives me -1. And then combining like terms, the constant terms, I have 7 minus 1 is equal to 6, and then minus the x squared minus the x. So now I have a polynomial. This looks like x to the n. This also looks like x to the n. It's x to the 1. And then I have a constant term. So now let's find the antiderivative. Also, before we do that, notice I've now filled in the limits of integration. We're going from -3 up to +2. So now back to finding the antiderivative. The antiderivative of 6, the opposite of the derivative of 6, is 6x. Again, we can check that. The derivative of this, 6x, better be this, and it is. The derivative of x squared comes from the power rule for antiderivatives. So that, recall, says increase the power from 2 to 3, and then divide by that new power of 3. And the minus sign comes along. This last term, negative x, which can be thought of as negative x to the 1, is also the power rule. So we're going to increase the power of 1 up by 1 to 2, and then divide by that new power. And again, the negative sign comes along. We are integrating from the lower limit of x equals -3 up to the upper limit of x equals 2. So that means we're going to have to substitute both 2 and -3 into this antiderivative, and then subtract those two results, which is what the fundamental theorem of calculus says. So you can see here I've done that. I've plugged 2 into the antiderivative over here in this left set of parentheses, and I've plugged -3 into the antiderivative in this right set of parentheses. And I'm just going to go ahead and do the calculation, and I may have to do a bit of fraction fixing and common denominator kind of stuff. But when I do all of that, I'm not going to go into that because I'm going to assume you can go back and do some fractions on your own. We end up with 125 over 6, which is about 20.833. So this represents the area between the red parabola that's below the blue constant line at y equals 7. We can see this in Desmos. Let's go over there. So I've set this up for us already. I'll go into projector mode. And so you can see y equals 7 is up here as a flat line. And then we have our parabola in red. And then the purple region is the area that we are looking for. And you can see here that I have the left limit of integration is -3, and the right limit is +2. And this computation, when I do that, when I take the integral from -3 to 2 of j minus h dx, I get the numerical value that we got through our integration by hand. All right, so notice here, if you define h and j the way I have here, then you can have Desmos do a calculation, so you can check your hand calculations. And so the way you could do this is you type in int to generate the integration symbol. You enter the left limit of integration, then the right limit of integration. Then in parentheses, you put in what you're integrating. So we're integrating j of x minus h of x. And this will not do anything until you type in dx, because that is required. So notice nothing happens here as a numerical calculation until I type in dx, and then Desmos knows to do the calculation correctly, because it's looking for you to tell it what is the variable. So it's not going to assume that x is the variable. It could be h or j for all it knows. So you have to tell it what variable you are integrating with respect to, and that's going to be the variable along the horizontal axis. So that shows you a little bit how you can use the technology to check your hand calculations, which we found over here.